topic that is related to the analysis of proper cantilever beam subjected to a eccentric point load. Coming to the problem, this is the question. Determine the reaction components for a proper cantilever beam subjected to a eccentric point load as shown in figure. Draw shear force and bending moment diagrams. So this is a proper cantilever beam AB. So here I am taking a numerical problem. So AB is having a span of 5 meters and the load here is 30 kilonewton, which is indicated by W. And this load is at a distance of 2 meters from the fixed support, that is A. And this load is again at a distance of 3 meters from the B support, that is a roller support. So this problem you are going to analyze and you're going to find the reactions first. After finding the reactions, then you're going to calculate the moment. Then you're going to draw the shear force, then bending moment diagrams. So before proceeding to that, first we will see what is the indeterminacy of the structure. So before finding the indeterminacy, first let us see how many reaction components are there at each support. As A is a fixed support, here you are having a horizontal reaction HA and vertical reaction RA, and you are having a moment MA. And similarly at the B support, as it is a roller support, it is having only a vertical reaction, that is RB. Therefore, the total reactions here are 4, and now the number of static equilibrium equations are 3 for 2 dimension. So as you know that sigma fx0, sigma fy0 and moment about xy plane is 0. Therefore, the degree of static indeterminacy will be equal to number of reactions minus number of static equilibrium equations, so which is equal to 1. So before going to see what is a redundant force, first we'll balance the forces. As we know that sigma fx is 0, as there is no any external horizontal load acting onto this beam, HA will be equal to 0. And similarly, summation of the vertical forces is 0. So we know that RA and RB are vertically upward. These are reaction forces. And these reaction forces are due to the externally applied load, that is 30 kilonewton, which is acting vertically downward. Therefore, RA plus RB will be equal to 30 kilonewton. So before analyzing this proper cantilever beam, I am assuming the beam to be consist of 2 parts. So first part is something like a simple cantilever beam with a eccentric point load. So this is a simple cantilever beam. And the second part is a cantilever beam with a point load at B support, that is at RB at this end. Therefore, this RB is considered to be a vertical reaction and it is treated as a redundant force. So before solving this RB force, in the next slide, we will see how you are going to find the deflection at the free end for a cantilever beam that is subjected to a eccentric point load. So this is a cantilever beam which is having a eccentric load at a distance A from the fixed and at a distance B from the free end. So for this beam, we know the deflection curve will be like this. So at the fixed support, we know that there is no rotation and there is no translation also. But at the free support, that is B support, you are having a deflection, that is delta B. So this delta B I am going to calculate first. So to calculate this, I am drawing another figure. You can see here. So as the load is acting at this C portion, so the deflection at this C will be equal to delta C, as well as there is a slope at this point. So the slope at this point will be equal to theta C. So that slope will be equal to this slope also, theta C. Therefore, the total deflection at this B portion will be equal to this delta C plus this delta 1. So we'll see what is delta 1. So I can write delta B will be equal to delta C plus delta 1. So we know that from this triangular portion, tan theta C will be equal to opposite by adjacent, that is delta 1 by B. Therefore, tan theta C will be equal to delta 1 by B. So, delta 1 will be equal to tan into theta C. So, as we know that this angle is so small, so tan theta C, I am writing it as theta C. Therefore, delta 1 will be equal to B into theta C. Now, when I substitute in this above equation, delta B is becoming as delta C plus B into theta C. Now I'm going to get this delta C and theta C. As we all know that deflection at the free end when the load is acting at this portion will be equal to WL cube by 3EI. So here L is nothing but A. So that is WA cube by 3EI. Similar way, theta C will be equal to WL square by 2EI. So here the span till the load is A. Therefore, it is WA square by 2EI. Now I am substituting in place of delta 1 as we know that it is B into theta C. So that delta 1 is becoming as WA square B by 2EI. So now when we substitute this delta C and delta 1 in the above equation delta B, so we get this expression. So we already know that L is nothing but A plus B. So I am substituting in place of B, it is L minus A. And simplifying the above term, I am getting a final equation of delta B will be equal to WA square by 6EI into 3L minus A. So this is a deflection at this free end when we are having a eccentric point load at this C position. So by using this deflection expression, I am going to solve the rest of the problem. So this is how we are going to derive the deflection for a cantilever beam when it is subjected to a eccentric point load at the free end. Next slide. In this slide, we will see how we are going to calculate the reactions. So as we know that consistency condition, so balancing the deflection at this B portion. So how you are going to balance this deflection is, first step, I'm going to make this proper cantilever beam into two parts as we discussed in the previous slide. So one part is a cantilever beam with a point. One part is it is a cantilever beam with a point load at this eccentric distance. So due to this point load acting here, so you are having a deflection, downward deflection at this free end support. So that is delta will be equal to WA square by 6A into 3L minus A. So that is as per the previous one. So this is a deflection formula. So that deflection formula I have written here. And we already know from this figure, W is 30, A is 2 meters, B is 3 meters, and the total span is 5 meters. So by simplifying it, I am getting it is 260 by EI. So after getting the downward deflection due to this externally applied load, now another part is you are having upward reaction here at this B support. So due to this upward reaction, I am having a upward deflection here. So this upward deflection is RB into L cube by 3EI. So this is your upward deflection. So as we know the consistency condition, that is net deflection is 0. So as both are in opposite signs, I am just equating the deflection part. So finally I get RB will be equal to 6.24 kilonewton. As we already know that RA plus RB is 30. So from this I am getting RA as 23.76 kilonewton. So this is how we got the reactions. So in this slide, we are going to calculate the moment. So before calculating the moment, I am just writing the RA reaction 23.76 kilonewton and RB reaction as 6.24 kilonewton. So now I am taking moment about this B portion. So while I am taking moment at this B portion, so this RA into L, okay, this is in clockwise direction about this point. So it is plus RA into L minus 30 into 3, which is in anti-clockwise direction. And again, minus MA. It is also in anti-clockwise direction about this point. So by solving the above and substituting the values of RA, L and B, I simplified the above term and I got MA to be 28.8 kilonewton meter, which is in hogging nature. So as we got the positive value, so the sign convention, whatever I am representing for MA is same. If I got the negative value, then I have to change this direction to be a clockwise direction. So as it is in this direction, that is in hogging direction, so I am representing in the bracket MA is in the hogging nature. So this is how we calculated the moment. So after getting the moment and after getting all the reactions, now we are going to draw the shear force diagram. So for drawing shear force diagram, first I represent all the reactions and moment what I got it earlier. Then we just draw this figure, that is proper cantilever beam. And then we are going to take a section in between BC first. So I'm starting with a B as an origin. So I'm taking a section in between BC. So here there will be two sections. Why? Because the load is dividing at some portion in the span. So therefore, we are going to take before load one, after load another section. So BC is the first section I'm going to consider. So shear force at the XX section is, this is your cutting section and which is at a distance of X from this B support. So this B support is a origin. I'm going to consider B as an origin. So therefore X is equal to 0 at B support, X is equal to 3 meters at the C support, and X is equal to 5 meters at the A support. So which is having from 0 to 5 meters. So before going to that, I'm just writing the sign convention here. So towards the section, when we have the clockwise shear, clockwise reaction, or then we'll call it as a positive shear. And towards the section, and if we are getting a anti-clockwise shear, then we'll call it as a negative shear. So by considering this sign convention, we are going to draw the shear force diagram also. So first I'm going to write the reaction here. So this RB towards this section is in anti-clockwise direction. Therefore, shear force at this X section will be equal to minus RB. So the limits here are 0 to 3 meters. Therefore, shear force at X is equal to 0 is minus 6.24 kilonewton, and X is equal to 3 also, it is minus 6.24 kilonewton. So this is when we are having a section in between B and C. Now coming to the next phase, when here we are going to take the section in the case of AC. So now I am taking a section in between AC. So this is a shear force section XX, and I am considering the X distance from the B supporter. So same sign convention here we are going to follow. So when you write here the shear force at X section, so this RB is in the anti-clockwise direction, therefore minus RB. And this 30 external load is in the clockwise direction about this section, therefore it is plus 30. So the limits here are 3 meters to 5 meters. So shear force at 3 meters will be equal to plus 23.76 kilonewton. Similarly, shear force at X is equal to 5 meters is also plus 23.76 kilonewton. So I'm just correcting it here. So this is plus value. It is not a minus one. Now coming to the shear force diagram. So this is a beam, we got it. And these are the shear force values, that is minus 6.24 kilonewton, 0 to 3 meters, and 3 to 5 meters, it is 23.76 kilonewton. So when we draw a figure at B, it is minus 6.24. At C also, it is minus 6.24. So this is a negative one. Again, from C to A, you are having 23.76, which is a positive value. So this is a positive shear. So as it is a point load, so we are having the shear force diagram like this. And next, coming to the bending moment diagram. So same, I'm going to write the reactions first here. And the moment here, it is a negative moment. I mean, hogging moment we are writing. And coming to this problem, so when I take section between BC first, so this is a section in between BC. So this is a sign convention. So when the arrows are heading towards the section upward, it is a sagging moment, that is a positive moment. When the arrows are heading towards downwards, that means the moment is a negative moment, it is a hogging moment. Now when I write about this section, when I write here, this RB is in the upward, towards upward arrow. Therefore, plus RB into X is the distance. And the limits here are X is equal to 0 to 3 meters. So when X is 0, at MB, the moment is 0. And when at X is equal to 3 meters, the moment at C will be equal to 6.24 into 3. That is 18.72 kilonewton meter. That is at the C portion. Now coming to the next phase, that is the section is in the AC segment. So when the section is in the AC segment, X distance from the B support. So what I'm going to do is same sign convention we are going to follow. Then when I write a moment equation here, it is RB into X, which is in the plus direction. Why? Because arrow is heading upward. So when I write another 30 into this distance will be equal to X minus 3. So which is heading arrow downward. So that means bending moment at about X will be equal to this RB into X minus 30 into X minus 3. And this is for the limit of 3 to 5 meters. Now, when we substitute X is equal to 3 meters, I'm going to get moment as 18.72 kilonewton meter. When I substitute at X is equal to 5 meter, I get moment as minus 28.8 kilonewton meter. So that is at A support. So after getting the moments here, we are going to find the point of contrafluxure. Why? Because the moment has the sign has been changed from positive to negative in CA segment. Therefore, we'll take the bending moment equation to be 0. Therefore, X I am getting it as 3.79 meter. So this is from B support, X is equal to 3.79 meter. The moment is getting changed from positive to negative. So at that portion, I'm getting the bending moment to be 0. So now drawing a bending moment diagram. So this is all the reactions I got. And this is the bending moment values I got. So this is ACB beam. At B, I'm getting a moment to be 0. At C, I got the positive moment as 18.72. At A, which is at 3 meters. And at A, I got 28.8 kilonewton meter, which is negative in the negative value. And at X is equal to 3.79 meter, I am getting the moment to be 0. So this is how we are going to draw the bending moment diagram. These are the textbooks and references. Thank you.